Good morning, good afternoon, good evening, wherever you may be. Thank you so much for joining Joel and I today. We're going to be presenting optimizing Kubernetes nodes the right way. Easy to say, not so much. We've got a great presentation lined up. We're going to spend a little bit of time in the slides. Joel's going to be doing a live demonstration, and then we'll wrap up with some questions and answers. Let's get into it. So the first slide really is around addressing the big gap. If you know Densify, you've seen this slide before. This is really how we talk and differentiate from traditional FinOps tools versus what we do, which is really optimizing supply and demand. So from a FinOps perspective, there are tools out there, free tools, enterprise bill reading tools that really focus on how you're spending your money in the cloud. Bill analytics, budgeting and forecasting, anomaly detection, purchasing, reserved instances, savings plans, etc. So that's the focus of those tools. That is not the focus of Densify. In a lot of cases for FinOps, they care about this, but they have very little control over how that money is being spent by the engineers and application owners. So you've got FinOps that cares about the money being spent. Engineering and app owners are the ones that control really how that's being spent. And our focus is really less on that analysis of the bill and more around optimizing the resources in use and addressing what we call the big gap. One of the ways that we focus on helping companies focus on that big gap, well, it's around correct sizing of the cloud instances, ensuring that you're running on the correct family, CPU optimization, the correct chipsets to help your applications the best, analysis of the scale groups and elasticity. And today's focus really is all around resource optimization at the container level, Kubernetes level, CPU memory requests and limits. That is our focus today, and that's what we're going to really be talking about in the next 20 minutes. So that big gap in practice, what does that look like? The DevOps folks building their applications, deploying them into the cloud, AWS, Azure, Google, and of course our focus today, Kubernetes. Finance folks will get that billing data, and you can see they become somewhat unhappy that the spend is high and they want to do something about it. Almost every customer that comes and talks to us says, you know, their key pain is really lowering that bill. But that often looks like just throwing that over that chasm, that gap, and saying, folks, this bill is high, let's do something about it. What does that conversation look like between FinOps and the application owners? Well, Kubernetes is expensive. You got to save money. Why don't you use fewer, smaller nodes? How about that? That would lower the bill. It's like, look, we need those resources. Smaller nodes could cause service outages, and that's the last thing platform and application owners want. But you're only using 5% of the resources. You know, what's going on? It's like, yeah, you don't understand how we use Kubernetes. And ultimately, why don't we see this point of view? You see this, and we've seen this, I guess, time and again, right, Joel?
Yeah. It's this disparity, depending on who you talk to. I've gotten reactions like, yeah, I think that gap needs to be much wider, because it's just really difficult when they have different ways of looking at the same thing. And so, yeah, without a baseline common understanding, it's miscommunication left and right. So that's what we'll tackle a little bit here. So
yeah, let's turn it over to you, and let's get a little deeper into the technology and the problem when folks set their resources too low or too high. So I guess now we're getting into the details of Kubernetes and the containers themselves, right?
Yep, absolutely. Thank you, Andy. Yeah, so to get down and kind of explain this, we need to find a middle ground or an understanding. So looking at beneath the surface of the nodes, what's running on the nodes, it's containers, so and pods and all that terminology, the great Kubernetes terminology that we so love. But if we just kind of zoom in on one specific container, and we've taken the approach of looking at the workload, memory usage, and we just converted it for simplicity's sake to a nice little Tetris chart. And so if we kind of apply that to a node, keeping in mind request values, so you've got the utilization in blue and requests. The requests are what developers have told Kubernetes they think they're going to use, whereas the blue is what they're actually using. And that's really the disparity there, because you can see the little Tetris block, in this case, memory usage over what they were expecting. Might not be a problem in some cases. The problem is if the node's under pressure, this happens. You get an out of memory kill. OM kill actually happens. There's a few different ways this could happen, but this means potential outage. And yeah, you know, it might be restarted and you might get more nodes, more costs, and Kubernetes is going to kind of handle that sort of for you, but it means users are impacted, at least initially, and more costs.
And so this is the risk side of setting those resources incorrectly, and that applications can get killed. I guess the other thing that we see, and probably, this is a bigger issue in a lot of ways for the app development team, but from a FinOps perspective, we see this other area even more commonly, and that would be with asking for too much.
Yep. So this is another example of a container that is over provisioned. So memory usage, not as much as they were expecting. So we converted it to the Tetris, nice little line. And so if we apply that on a node, and let's say this is a sizable memory usage, you've got the request being over provisioned. Well, if you run 2 of them on that same node, what you get is, of course, the utilization. That's the total utilization. Well, this Kubernetes scheduler doesn't care. It doesn't look at utilization. It looks at those request values, the values that the developers said that they think they need. This is the root problem, because this is how you get the overspend and the underutilized nodes. It's because this happens at a grand scale. You have hundreds and thousands of these things running. This is how you get a node that's underutilized.
And I guess in a lot of cases, 50% would be great, but in a lot of cases, we're seeing, just like the FinOps example earlier, 5%, 3%, even lower, right?
Yeah, we've got some nice examples coming up. The problem is this can happen in the same cluster, right? You have multiple nodes. You can have a node that's you're running out of resources, and another one where there's like no resources being used. Very, very difficult to get right, because you got to get down into each container.
Okay, so let's talk about what's driving the high costs here. What is this telling us here, Joel?
Yep, so that's the problem. So we've outlined the problem. How do we get visibility, even at high level, to know how off are we, right? So we've got, this is a real screenshot of the utilization. So this is what's actually being used. And you can see 4% on average, kind of spikes up and down, it hits 20%. But on this cluster, this is a cluster view, the resources are almost idle. So of course, if I put on my FinOps hat, the resources aren't being used. Guys, we're overpaying. Why are we doing this? And of course, that's because it's utilization. No visibility into what's happening under the covers. And so if you look at the requests, again, same screenshot here, but looking at requests, it's at 95%. So it looks like they're requesting the right amount, more or less, at least the max amount. Problem is, it doesn't match when you look at the utilization. So the developers, the engineers, the platform owner for Kubernetes, they're going to say, look, FinOps, you don't get it. They need it. It's because of all the engineers. We need these resources. Otherwise, things are going to be turned off. Okay. And yeah, we'd love to optimize the nodes to get them lower, but this is really difficult to get right, because it's not just one setting. It's many, many, many containers that are either over provisioned, under provisioned, and very difficult to get right. So while I'd love to optimize the nodes, and we can get there, we can only do it after we fix the container request values, those CPU and memory requests.
Let's talk about an example here. It's a real live example of some of the recommendations that might come from the free tools, or in some cases of a real enterprise bill reader, so to speak.
This actually comes back to the same screenshot in the previous slide, but if we compare the utilization and the request from before, that was running on 14 nodes on AWS M5, 8 extra large. So you can see the specs per node there, and doing simple math, those specs times 14 nodes, that's how much total resources are available at this Kubernetes cluster, within the cluster. So from a costing perspective, again, basic math, nothing fancy here, roughly just under 10K per month for this one cluster. And so they were looking at a typical, another tool, FinOps tool, that gave them a recommendation to say, utilization is so low, you can shift it down from an M5, 8 extra large, down to an R5A 2XL. R5, well, that's memory optimized. So that's going to add more memory, but it's a smaller instance, right? You're getting way less CPU, less memory, should be cheaper in theory. Doing math there, of course, you get less resources, but if you look at the costs, oh yeah, I would take this recommendation on the surface, because it looks like we're going to save 70% of our costs. Awesome. Why don't we do this? Well, this gets into the problem. Those tools have zero visibility or understanding of what's actually happening at the Kubernetes level, at Kubernetes scheduler. If this customer was to switch to this R5A, they would actually have to run 55 nodes approximately, because they need to get the same or similar number of CPU cores. Coming back to the screenshot previously, that cluster was CPU bound. If they were memory bound, we'd be having a slightly different conversation, but the same. They would still need a lot of nodes. In this case, they need about 55. Otherwise, you won't have things running, never mind out of memory, you just will have pending pods. Nothing will run. And your engineers are going to be, who are they calling? They're going to be calling the platform owner, and the platform owner is going to say, I'm never taking a recommendation from this tool ever again.
The other
Oh yeah.
interesting component there is the memory, right? I mean, we weren't using the memory before, it was CPU bound, and look what's going to happen if you take this recommendation, right?
Yeah, you're running many more smaller nodes. You're getting a lot more memory for no real value in this case, because it's going to be well underutilized, and your costs are going up. So they took a recommendation that was supposed to lower the costs, and it ends up raising the costs. If I was a platform owner, I'd look at this and be like, this is a good example as to why I will never listen to this tool again.
And we see that as well a lot of times where customers talk to us about the fact that they've made bad recommendations and now they can't get the attention of these folks back again, the folks that control these resources.
That's right. So the best way, the right way to optimize this is you got to go bottoms up, and there has to be a little bit of strategy. So the ones at risk, the containers that are at risk, these are ones where the request values are lower than expected. These are the ones we need to fix first, because they're being propped up by the ones that are oversized. Strategy, eliminate the risk, fix those first, then you can reduce the waste. The ones that are way oversized in CPU and memory, now we can fix those. We can right size those, and we have different ways. I'll talk about how we can do that. But once that's done and your containers are running optimally, then you can look at actually optimizing the nodes, maybe switching to a memory optimized, the CPU optimized. Then you can actually get into that and optimize them and even reduce them as well. Because if you're reducing those request values, you might not even need, those 14 nodes or however many you're running ultimately.
A quick shout out to marketing. This is an interesting download we have around 12 risks in Kubernetes environments. And that's where these graphics are coming from, container nodes that are either overwhelmed with undersized containers or sitting there fat and happy with almost nothing running on them. So that's where those icons come from.
That's right. You want to make sure you're using what you're paying for. I want to keep it short today. We've got nice dashboards. We've got different ways of breaking down the data, but I want to get right into the recommendations and talk about, well, what can we do about it? How can we tune them? This is the Densify UI. I've logged in. I'm looking at container right sizing recommendations. We're looking at the CPU and memory requests and limits. For the purposes of today, let's just focus on requests. The request values are, again, what the developers have said that they expect they will use. What this is showing us is that for CPU, for example, I've got across my whole, I got 4 clusters in here, so many containers, container manifests. I've got 68 of them here that are over 5 times bigger than they should be for CPU requests. So if I wanted to reduce my waste, I'd start there, really easy to get into. Likewise though, in the same cluster, we've got 16 and another 74 that are 80% smaller than they should be. So if we're talking the ones at risk, those are the ones that I'd fix first. The request values aren't high enough. So if you start reducing this, these ones might be affected because now the nodes are going to be more under pressure, and those ones that are over or under allocated on request values, the nodes might go, well, I don't have space for you. You're over your request value. Either fix it or go to another node, and you get out of memory errors. That's why you got to fix those first. So let's look at these ones here. I'll pick on one here. So I went from the analysis into the details, and we can get into the details here across all of our clusters, and I've sorted it down, and I'm going to focus in on maybe this web deployment one here. So got web deployment, web container, and you can see the current values and the recommended values. I don't have time to get into how to tune the policy here. I can spend a whole other 30 minutes on that, but just suffice it to say that yes, our policy engine is extremely customizable. You can have, for example, a different policy for dev or test environments, a different one for UAT, and then even a different one for production where you want to be more conservative and not be so aggressive bringing the bar down. Maybe you want to do it in stages, all very tunable with the policy engine. You can have as many policies as you want. So let's just assume for the time being that these recommendations are correct. Okay, you can see them down below. I can click on these and I'll get the workload graphs for each of them down below, but I'll stick to this one here. CPU, So I've got CPU request and limits. They're both set at 2. This is millicores, so 2 CPUs for this one container. It doesn't even use half a CPU. And this is over the course of 2 or 3 months, all defined by policy. This is not the last 24 hours. This is months of data. You can see it doesn't even reach half a CPU. Why? Why do we have it so high? Well, it's because it's difficult to get right. So you've got the recommendation here. It's already made the analysis and it's saying you can reduce it down, CPU requests down to 400. That's what it looks like visually. Yeah, recommended CPU requests. And so we can do that. We can reduce it down. We can, so far, we've only got the recommendations in here. There's a number of ways that we can take them and either automatically apply them, or for example, I can download it, put it into a BI report, integrate it with ITSM. We've got an integration with VPA where you can take our recommendations and in a scoped and controlled and scheduled way, apply them automatically, let's say during your maintenance release, where it's maybe every 2 weeks, every week, every month, every quarter, whatever it is, you can schedule that, or even just add it in as an annotation. Don't make the change, but take the recommendation, put it in front of the engineers that can actually make it themselves. For production environment, I would personally like that, because then in production, as an engineer, I'd be like, oh, wait, I can resize this? Okay, I'll schedule it in during the next maintenance release, but then it's fully controlled and maintained that way.
Hey, Joel, sometimes in a Kubernetes environment, we're saying, well, we're talking about like really small amounts, that we're talking about half a CPU of savings or half a gig of memory savings. It's like, who cares? Like, that's not very much for this one example you're giving me here.
That's true. This one only runs one. Maybe a bad example. How about this one here where we've got an analysis container. There's 30 of these things running and it's oversized in both CPU and memory we've got requests and limits set at 8 gigs of memory, not even using 5, So a good example of, hey, even CPU, we can reduce it down by more than one full CPU. If I've got 30 of these things running, depending on the node size, that's one whole node. If I fix this one container, I can just reduce my node spend by 1. So no matter what kind of auto scaling up and down technology you have, they're going to help mitigate kind of the symptoms, but they don't actually solve the root cause of over provisioning, underutilization, all of that. You have to get down into the container analysis.
And at scale, it's interesting, isn't it? I mean, we've got some customers we're talking to right now, and a recent one where 400,000 or 500,000 containers running in their environment. Another one, over 1 million containers across their estate. This is an enterprise-sized customer, but start getting into setting those things incorrectly and trying to do it by hand. It's like you're never going to fix it, and the impact is potentially just astronomical, really.
Yeah, exactly. That's why you need to have multiple strategies for dealing with that. Break it down by environments, by clusters. Dev cluster, why should engineers have to manage this manually in development? Just have it automated. And for production, maybe you want to put it in front of them. So you can do that by adding automated annotation. Easy to do.
So let's wrap up. Thanks for the demo, by the way. That was great. And of course, if you've been watching and you say, I want to see more about this, we've taken some liberties. It's not a full-blown demonstration, just very specific to the point we're making here today. But if you're interested in seeing more and a little bit slower, less of a New York style demonstration, we'd be happy to set that up for you. Number one, we see the cloud costs, especially in a Kubernetes environments, are typically driven by underutilized nodes, setting these things and using 5-10% of the resources. Why are they underutilized? Well, they're really a result of the oversized containers, as Joel was showing. There's some risk in there, but for the most part, 80% of the problems we see in there are just not using the resources that you've reserved. Joel, what do we do first?
Fix the containers, fix the risky ones, then reduce the waste.
And we have found that the free tools, and there's lots of them out there, and they do a good job of what they do in terms of visibility into what's going on in the cloud spend. They just don't solve the issue, or even worse in some cases, they actually give recommendations that are implemented once and never trusted again. And we see other tools available from Kubernetes or open source community, what have you, where those auto scaling tools are there, and they're important for what they do, but they also don't fix the issue. Densify, we continually right size these container resources, fix the risk, fix the waste, and then make that optimal node instance recommendation. So if you try to start with the nodes without fixing, the root of the problem, that's where we see companies coming in to a lot of challenges, a lot of issues. I wanted to talk for 1 minute about a great partnership we have with Intel. Intel has created what we call the Intel Cloud Optimizer program. So that's a program, it runs using the Densify software, and Intel sponsors a full year for qualified organizations. So not every company will qualify for that. You have to have a minimum amount of infrastructure. It's an amazing program, really, in a lot of ways, because it allows you essentially 12 months to figure out how well will this fit into your FinOps initiatives, your cloud initiatives, Kubernetes savings optimization initiatives. Scan that QR code or just go to our website. You'll see it's right on the main page. Look for Intel Cloud Optimizer. Great program, and we've got some amazing success stories we'd be happy to share with you about that. Resources, questions from the audience, let's take those things now. In the meantime, we mentioned those 12 risks. There's the link for that. And then we also have a really handy Kubernetes guide available on the website as well. Just one question in there, which is probably good because I'm just keeping an eye on the time here right now. Joel, I'll paraphrase it, but essentially, what's the difference between Densify and these open source tools like Carpenter? And it sounds like, we do come across some things like that in vertical pod autoscalers, but specifically on Carpenter, can you just provide a minute of differentiation between what we do and what those tools do?
Yeah, I'd say we actually work very well together. So there's lots of autoscalers out there, whether it's HPA, VPA, or cluster autoscalers like a Carpenter, which works great for what it is, right? Which is auto scaling up, for example, and even scaling down of the nodes. That is important, but that doesn't directly address the root cause. You still need tools to go up and down, but if those little grains of sand, whatever analogy you want to use, if all those running containers are oversized or at risk, if they're undersized, it does not, you can scale up and down, but you still have challenges. You could still have out of memory errors. You can still have, CPU being throttled. So they're very complementary. We don't replace them. They don't replace us, but they really tackle different challenges. That's where I'd place it. You still need something to solve the right sizing problem of all your running containers across all your environments. That's where we help fill in.
One more question about the Intel Cloud Optimizer. Is that just for AWS? It's like, no, actually, that program is designed for customers running public cloud infrastructure, AWS, Google, or Azure. And for some qualifying organizations, we look closer at the Kubernetes piece, but we can get sponsorship in some cases, as long as there's infrastructure as a service components running as well.
I just hope this has been useful and valuable for everyone on the call.
Thank you to everyone who attended today. Have a great day, and we will be talking to you soon. All the best. Thank you.
Thanks. Cheers.